it's 11:30. Hello, everyone. Welcome to the second lecture of the Geo-Institute of Colorado Expert Lecture Series 2026. My name is Shahbaz Ahmad. I'm the chair of the Geo-Institute Colorado, secretary of the Denver ASCE branch, geotechnical engineer with Kiewit, and your host for the day. It's truly nice to see such a strong geotech community we have in Colorado. Our goal with the Expert Lecture Series 2026 is to bring globally recognized leaders in geotechnical engineering to Colorado and help build a strong connection between industry, academia, and young professionals. Our inaugural event with Dr. Hashash went really well. So those waiting on their PDS certificates, we are working on it. So I really appreciate your patience on this. For today's lecture as well, we'll be having the PDH. There'll be a short quiz, so take some notes while Sir is presenting. And look at your faces. There's no quiz. All right. So a little promotion here. So if you guys can take your smartphones out, scan this QR code, I'd really appreciate. This is to get all the updates and the events for the coming events this year. Moving ahead, I'd like to thank my team for Geo-Institute of Colorado and ASCE Denver branch. They have been a big help. So if you see any of these faces today, just say hello to them, introduce yourself to them. It'd be nice. And some of the faces are not here. I'll mention Nick Chipolati, Hunter White, and Becky Umlin for helping me. As a good host, I'd like to thank our sponsor, Kiewit, our event sponsor, Night P Soul, our gold sponsor, Terracon, our bronze sponsor, and thanks to Cage for supporting the event. Without further ado, I would like to introduce the speaker of the day. Dr. J. Carlos Santamarina is a professor and clock chair at the Georgia Institute of Technology. He earned his undergraduate degree from National University of Cordoba and completed his graduate studies at University of Maryland and Purdue University. He has held faculty positions at NYU Polytechnic, the University of Waterloo in Canada, King Abdullah University of Science and Technology in Saudi Arabia, and Georgia Tech. Dr. Santamarina is internationally recognized for his groundbreaking contributions to geotechnical engineering, geomaterials, energy geotechnology. His research combines experimental and numerical methods to better understand the behavior of sediments, fractured rocks, complex fluids, with applications ranging from offshore and energy infrastructure to subsurface characterization and emerging geotechnologies. He is also one of the most respected voices in our profession, having delivered some of the finest and the prestigious lectures in and around USA, including Terzaghi Lecture, Casa Grande, and Bishop Lectures. In recognition of his impact on geotechnical community, he has received numerous international honors and awards, including ASTM's Hogan-Togler Award, the Korean Geotechnical Society Award, the Saudi Arabia's Tariq Al-Kasabi Award. He is also a member of both Argentine and National Academies. And yes, he has a Wikipedia page as well. I just saw it this morning. Really cool, sir. So please join me in welcoming Dr. J. Carlos Santamarina.
I'll set here and reduce this. Excellent. Well, good morning, colleagues, and thank you so much for coming here with this rainy day today. It is, sorry, I have an echo. Let me see if I can resolve that. Hello?
You need to mute
yourself. Yes. Okay. So this is a lovely room. The weather is not the best, but it's wonderful to be together. And by the way, I'm inspired by all the quotes around us, including the last one there on the bottom part, that if we are constantly learning, we will have a long-lived company. We will be able to adapt quickly and to adapt quickly to the changing environment. And this is where we stand today. Things are changing, and we need to adapt, and we need to continue learning. And so in the spirit of that, consider the presentation today as a step in that direction. Okay. Consider this as a challenging question to begin with. Geophysics has been promising for the last 60, 80 years to make a difference in our profession in geotech, and we have to wonder whether that has been the case beyond some specific niches. On the other hand, let me say that if it wasn't for geophysics, we wouldn't have petroleum today. Supercomputers were developed not for medicine or Department of Defense. Supercomputers were developed to analyze geophysical data for petroleum. And so it has had a huge impact in our lives in many ways, but we have to look back into our profession and wonder what is the status. So if we begin looking at trends, let's start for what do we really need to get from any type of characterization. We need to get the type of soil, the density, the stiffness, the strength, transport properties for coupled processes. If there are fractures, and by the way, this is a big space, particularly if you're in Colorado, fractured rock masses, what do we need in that case? The fracture sets, what are the preponderant fractures, the governing ones, etc. Of course, we still need the stiffness, the strength, the anisotropy in the properties. In all cases, we recognize more and more the importance of understanding spatial variability. And as it turns out, classical geotech doesn't do all that well. We tend to be very local. It's just the point where you do a CPT or an SPT or boreholes. These are localized measurements at a given time, and we use extensively empirical correlations. So where does near surface geophysics come in is really to contribute the spatial variability. An assessment of the spatial variability, it is minimally invasive, which tends to be much less expensive than costly drilling campaigns. And it has the potential to be used extensively for monitoring the performance of a system for the long time. I will come back to this slide as we come to the end of the presentation, but if you look at these two descriptions, we realize that there is a potential paradigm shift here taking place from sparse point measurements to being able to determine the spatial temporal multiphysics characteristics of the subsurface, getting these subsurface models. So that's where we're going to go, but I would like to highlight today the word multiphysics, because that is where I'm going to emphasize the presentation today. What are the parameters that we actually measure? To start with that, we need to recognize what are the materials that we are testing. And so this may be trivial, but let's go back and realize the sediments come in all sizes and shapes. And the coarser grains have a different genesis than the finer grains. The coarser grains come from mechanical processes, but there is not enough momentum in small particles to crash and break down. So small particles are not formed mechanically. They are the process of bioprocesses, diatoms for aminifera. They are the effects of precipitation. All kaolins are chemical precipitates. All kaolins, all clays are chemical precipitates. And we also have thermal processes, the fly ashes. On the mechanical side is where particle shape gains relevance from the point of view of mature sands versus fresh sands. But also the forces that govern these sediments are completely different. And this is what we really need to understand, the genesis and the forces. Capillarity is not relevant. You can make up to sand castles with sand, but that's it. Capillarity gains relevance for smaller components. Electrical forces is like the dust getting stuck on our furniture. That is where electrical forces begin to gain relevance in the submicron particles. Now, the other component that we don't emphasize enough in our courses is, if you come from with a degree in civil engineering, we call the course soil mechanics. We have to change the name. That was good at the time of Terzaghi. We have to move beyond that, is soil processes and properties. And so we really have to emphasize more the properties of the fluids within our soils, because that is where the most exciting applications are evolving. And so let's start by understanding water. And the only reason why we can use the microwave to heat up water is because water is this dipole. And the whole plasticity of clays is because water is a dipole. If you mix clay, don't do that. We used to, but now it's a carcinogen. With carbon tetrachloride, which is carbon, chlorine, 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 it's a symmetric molecule. It feels exactly like sand. We used to do that in class, but we are not allowed to do that anymore. So if you mix clay with a non-polar fluid, it feels like a silt, like a sand. The plasticity of clay is all about this dipole, the water molecule, the same reason why we can warm up the water in a microwave oven. And because it is a dipole, when we add table salt, it becomes salt water, which is all the water hydrating the sodium and the chlorines, and these hydrated ions can move. This is the essence of electrical conductivity. So when we talk about electrical resistivity, tomography or measurements, etc., this is what we are talking about. But then many of our subsystems have mixed fluids, which could be typically air and water, but could be N-apples, D-apples, oil, gas, hydrogen, methane, CO2, whatever we're trying to store in the subsurface. These are mixed fluid conditions at the interface. The molecules are not happy with the mismatch, and that is where they form interfacial tension, and you remember the contact angle, and that is the essence of unsaturated soils. But then there are phase transformations. Water becomes ice or vapor and can form hydrates. This is fascinating space. We don't teach this enough, but we will need it today. So today I'm going to go through different geophysical methods, not how do we implement them in the field. So we're going to try to emphasize, for me there is something fundamental always whenever we do measurements. What we measure, what we want to measure, what we think we measured. There are three different things. And I want to make sure that we understand what we measure and what we want to measure with geophysical techniques. Because once you understand that, and it may be overwhelming today with all the slides that I'm going to present, but they will be there for you. Once you understand that, it makes so much more sense to realize why geophysics can lead us to this paradigm shift. So I will cover mechanical waves, X-rays, X-rays too, thermal, electromagnetic, and nuclear magnetic resonance. Let's see if we move this forward. So by the way, one of the problems with geophysics, there are lots of these physical processes going on, so you have to use your brain a lot. And that is the last part. I will say something about that. So let's start with mechanical waves, and there are two types. If you have a series of penduli hanging from a roof, and you move one transversely to the alignment of all the penduli, and they are connected with rubber bands, let's say, so this transverse perturbation will propagate in the x direction, and that is a shear wave. But if you move the first penduli in the same direction as the direction of their alignment, this perturbation also propagates, but the particle motion is aligned with the direction of propagation. That is P waves. So we are going to try to understand these two. And how do we measure them in the lab? For very small strains and quasi-static test, that means that the wavelength, the frequency becomes very low, the period is very long, the wavelength is very long. That is a quasi-static test. We can put local displacement transducers in triaxial tests, let's say. Then we can do resonant columns. That is the longest wave that you can do dynamically in a specimen. And then we use, for example, Bender elements of piezo crystals. Now the wavelength is much shorter than the specimen, but it has to remain much longer than the particle size. So there is a window that you can operate understanding what you're measuring. For fractured rocks, that window becomes very tricky because you need to have many, many blocks, and that is what these two guys are disassembling from a true triaxial. You need to have all that large number of little blocks to understand wave propagation in fractured rocks. The box has to be much larger than the box has to be much larger than the block size, and the wavelength has to be larger than the block, but smaller than the box. Oof, very tricky. So we don't know much about wave propagation in fractured rocks. It may surprise you, but I'll be happy to discuss that further. So now let's talk about shear waves and its physics. That is geophysics. Where does the physics come from? From Newton, F equal ma. This is m, this is acceleration, and this is the force. F equal ma. This is Newton in differential form, and it anticipates the shear wave will be proportional to the shear modulus divided the mass density. Now, folks, this is it. This is the main link that we have today between geophysics and geotechnical engineering. This is the most successful story in this link of bringing geophysics to geotech. Why? Because the shear wave doesn't propagate through the water. And therefore, you're really testing the skeleton. You're asking the granular skeleton, how are you feeling? You send the wave, and you pick it up from the other side, and it gossips. It tells you what it found. And so we have used it extensively to get the small strain stiffness for settlement computation. We don't do enough. I think that this is very important. The dynamic response liquefaction, VS30, the average velocity in the upper 30 meters, is what determines the site amplification. So lots of people in the seismic soil dynamics have embraced this, and therefore we have developed lots of field techniques which are truly quite powerful. So this is the main success story. By the way, if you think of measuring the small strain stiffness, think of the stress-strain curve, starts steeply and then goes asymptotically to the strength. And so we don't need to know too many details about the shape of the curve, but we want to get the two asymptotes right. One is the strength, the other one is the small strain stiffness. Small strain stiffness, shear wave velocity is it. Really, we have to use it more. Strength, oh, go ahead with CPT, SPT. You're breaking the heck out of the soil. That's a strength. Don't expect to get strength from penetration testing. I mean, you can put a geophone and send waves, but not from the penetration testing per se. So look at what we can do. For example, we can put two transducers beneath the pavement. Great opportunities for all the infrastructure reassessment and reutilization. We put two transducers beneath the pavement, and then we send waves, and we see when a truck comes, how the wave propagation time decreases, and then the truck passes by, and the wave propagation time increases. It's feeling the stress. And why is that? Because when grains are in contact and you squeeze them, like squeezing a soccer ball, the contact gets flatter, and if the contact gets flatter, the stiffness gets higher, the velocity is higher, the propagation time is shorter. So you are measuring, in a way, you are measuring the state of stress. Very powerful. And how is it related in different soils? This is clay. Somewhere here you have Mexico City clay, remolded Mexico City clay, one of the weirdest soils in our books. And then you go into the silts and the sands and the cemented sands. This is the relationship between the velocity at 1 kPa average stress, 1 Pascal average stress, to the sensitivity to the state of stress beta. Quite predictable. Not enough for design, but it tells you where things are going. Now, let me give you an example. Imagine that I put, instead of using an inclinometer, I'm going to put two geophones behind a retaining wall. And I knock the wall, and I send the wave, and I measure the travel time. And I'm going to move the retaining wall back and forth. When I move away from the field, the force decreases. I had the force transducers here. The force decreases, the velocity decreases. And I go towards K active, right? And then I push back towards K passive. The force increases, the P wave velocity, shear wave velocity increases, and then it decreases. Not a bad sensor of stress. It's a little weird. Stress is a tensor, this is scalar. It gets more interesting than that, but that's what it's measuring, the flatness of contacts. Now, contacts may become stiffer not because you have squeezed them, but because they have been together for such a long time that they have flattened just by creep, or because minerals have precipitated at contacts. And so, for example, this is a dry sand with a little bit of bentonite, and typically there are always salts in our water. We begin drying it, and I could show you the salt water characteristic curve would match this. But now I'm measuring the shear wave velocity. As I begin drying it, it does air entry. The suction doesn't increase much until it hits the kaolins that are in the pores, and then the suction increases, the shear wave velocity increases, and then when it is already very dry, any excess salts precipitate. And because the excess salts, at that point, any remaining water is penduli between contacts, the excess salts precipitate at contacts, and it has a huge effect on shear wave velocity. Case history, Dick Woods, some of you may recognize the name. They were doing some geophysical measurements for a nuclear power plant in Brazil. They measured during the dry season. They had very high velocity. They did the design just in case they verified the values. But this time they did during the wet season. The velocities were completely different. You pick up the effect of suction and cementation and salt precipitation quite effectively. Now, the other thing that you pick up is that even if the material is totally saturated, when you take, let's say, fly ash or tailings, and they are fresh, they are very active, chemically active. They just went through melting or crushing. And so when you leave them in a bucket full of water for a while, early diagenesis takes place. And let me show you, this is fly ash in a bucket, no stress, 2 bender elements. Let's measure the shear wave velocity, 5 minutes, 35 minutes, 1 hour, 2 hours, 4 days. The travel time gets shorter and shorter and shorter. No excess pore pressure, no changes in effective stress. This is early diagenesis. The velocity increases a lot. So whenever you place these materials, and then you wait until the next layer comes on top when you're doing your ponds, your sedimenting them. By the time the next layer comes on top, it may have experienced some diagenesis. And this lower layer will not consolidate as much as you thought it would, because it locks in porosity, which makes it very brittle. And then maybe, there are different hypotheses for this, but maybe you can begin understanding and explaining the Kingston fossil plant failure that already is amazing, but it's already 18 years ago. Yeah? And we were working with Bob Bacchus during Christmas Day that because of that plant. And tailings, Brumadinho in Brazil. I think that early diagenesis is very important, and shear wave velocity is the one that can tell us the story more than any other measurement. Now, there is a problem when soils get cemented, and then we like to do laboratory tests, and you sample them. Let's follow the case. This is a soil that we stressed, then we waited for a long time, and it got cemented. So it's like 2 soccer balls. You squeeze them with crazy glue in between. And then you relax it, they stretch up, and the crazy glue breaks. That's what we do every time we sample soils. We break the contacts, and it doesn't matter how much you squeeze them back. And if you go to Chanceps, MIT Chanceps or whatever, that cementation is gone. So whenever you measure velocities in the laboratory or in the field, you will see a difference. And that is because that loss of cementation. Sampling is torturing to the soil. Don't think, this is non-destructive, how do you call non-destructive sampling, or there is no such a thing. There is no such a thing, and we change the state of stress. Even if in a block sample, Borslov and all go back to the history of the field. So now we can do some engineering thanks to these small strain modulus. This is where the Vogel plant actually came up in Georgia. And this is actually on the Savannah River National Lab. And so we have settlement data, etc. We measure the shear wave velocities, we have the data. You have to use a little bit of a modulus degradation reduction, but you start with the shear wave velocity, with the stiffness from the shear wave velocity. You degrade from a strain progressively, and then you predict the settlements, and it's the best way to anticipate the settlement of large structures. And you can link back to Ken Stokes' work, to Berland's Small is Beautiful, Suzanne Lacasse at NGI. The evidence is there. Let's embrace it. Now, we've been saying a lot about shear waves because shear waves are really one of the most successful stories of geophysics in geotech. But it's important to see the other components as well. Let's see what P-wave can tell us. So this is a little bit of a zigzag, but P-wave, can you see? Oh, yes, sorry, it's hidden in my case. But P-wave is a constraint modulus. When you squeeze the soil, zero lateral strain, that's a constraint modulus in the odometer, because the P-wave is a plane that is advancing, and so it's a constraint modulus over the stiffness of the soil. And so now we can begin doing a little bit of zigzag. The constraint modulus is the bulk modulus of the suspension plus the skeleton. The suspension is the grains plus the fluid. The fluid is water plus air. And so you concatenate all these. You do the same for the mass density, just pure algebraic relationships, and you can predict how this P-wave velocity will vary. And one thing that you realize very soon is that the P-wave velocity, now this is now doing all the substitutions, the P-wave velocity is very sensitive to the degree of saturation. So the best way, I mean, you can go back to Skempton's B parameter, right? When you do your testing and you want to make sure that it's saturated, you can check Skempton's B parameter, you can check the P-wave velocity with two piso crystals. And if you're not close to 1500 meters per second, you don't have full saturation. And that is very important because then Ishihara and collaborators realized that in many cases, we cannot measure the B value very well to determine the cyclic stress ratio, but in the field, we can measure the P-wave velocity. And if the P-wave velocity begins dropping, the chances of liquefaction are going to begin decreasing. This is not to say that unsaturated soils will not liquefy. Saturation is a weird thing. It forms patches, but it's a very good indicator of the possibility of saturation. P-wave velocity is great for sub-bottom profiler if you are working in lakes or offshore, or it tells you what is happening, the bathymetry, what is there, and what is happening beneath the formation. It's amazing. Eh? Think of watching the baby with ultrasonic imaging. It's the same done in the field. And this is to tell you that if you have good profiles of P and or S wave velocity, this is for deep boreholes around the oceans around the world, you can begin anticipating what type of soil you have. And from there, you can begin anticipating your compressibility and the burial densification, et cetera, et cetera. And if you think of VS30, you will be integrating this upper part here. Enough of mechanical waves. I'm going to move on now to X-rays just to say a couple of things. Very cheap. It used to be expensive. In fact, we used to go to the medical centers to get X-rays from our specimens. But in general, we run very expensive tests from very expensive cores. Some of the cores we take from the bottom of the ocean were probably more expensive than their weight in gold. They were $1 million per core or whatever. Eh? So, and then we had them as if they were perfect cores. It's important to get an X-ray before you do that because it will tell you quite a lot what is inside, the structures, the fact that gas came out. There's always gas in the water under pressure, but then the gas comes out to solution, like when you open a Coca-Cola can and it expands the soil and breaks the soil. In extreme cases, what you get is chocolate mousse. It's totally destructive. So it's nice to see, and you can see the bending of the edges. That is the effect of sampling. But you can also see the layering, hydrates in this case. This is a little bucket with kaolin, and I put it in the freezer. I looked at it the following day, and now you can see all the ice lenses forming in very characteristic patterns, and how it evolves towards the center. This is called cryogenic suction. It sucks the water and consolidates the center. This is important for the upper parts of Colorado and North America. You can also see the navy bean growing. Now, in this case, we made the soil X-ray. The soil is there, but for digital signal processing, we remove the sand, and you can gain great information. The group in Grenoble actually went further, and they gave a name to each particle, and they follow it during triaxial testing. And they could see how they were moving, rotating, displacing, shear band formations. It can be incredibly insightful for academic work, but most importantly, for industry work. We run very extensive tests. I think it's critical that we do X-rays, and we can do them really quite inexpensive. I'm going to say something about thermal properties because it's gaining relevance in our field, and for the near surface and deep. So how does temperature or heat propagate in our materials? If you have an electrical conductor, a piece of copper, for the same way that electrons can move fast, thermal heat can also move fast with the electrons. So metals, good electrical conductors, good thermal conductors. That has nothing to do with salts and rocks. There are no free electrons in our systems. So what is happening is that with temperature, everything is vibrating. But things are not going that wild, because if this is vibrating, the neighbor, remember that there is a bond between, the neighbor is moving together with it. So there is some synchronicity in the movement that is called a phonon. And that's the way heat moves. It looks like a wave. And it's a wave for random excitation. Yeah, it is, because of this synchronicity. And you can see this moving. I don't know if it is perceptible. Yeah, it's perceptible. This is a phonon actually taking place. So how do we measure that in the laboratory? You can do it in a very simple and very robust way. For soils, there is something called an electrical needle. You put a little resistor and a thermocouple, you heat it up, and you see how the heat escapes just by monitoring at the center. Very smart. And it almost looks like a hypodermic needle, right, that you can punch into the odometer, into triaxial. For rocks, that is more difficult. You could drill a small hole and then put some conductive, but it's not good. So for rocks, we make a stack, and we put a hot plate, a cold plate, thermocouples, and we see the gradients between different phases, and we measure the thermal conductivity and the heat capacity, etc., very effectively. Let me tell you, the story is very simple. I'm going to show you data, but the experience for the kitchen is much more relevant. If you're going to grab a hot pot, we don't squeeze tight. We go kind of fiddling with our fingers, right? And second, we don't use a wet cloth. That's it, folks. Thermal conductivity is all about contact stress and water. With that in mind, this is thermal conductivity of a dry sand. Increases with the state of stress, but look when it is saturated. It's a huge jump. That is grabbing with a wet cloth. By that point, even if you squeeze hard or not, you're already getting your fingers burnt. Okay? The thermal conductivity is already very high. And by the way, if the soil is unsaturated, you don't need much water to improve the contacts between particles. You just need water at the contacts. That's enough to bridge the gap. So with a little bit of water, low degree of saturation, you have a big jump in thermal conductivity. So unsaturated soils will have a high thermal conductivity. And why it is important for the near surface? Because now we're using these thermally active foundations, whether they are piles or big slabs, mat foundations, and retaining walls. and tunnels. We're extracting heat from tunnels. And by the way, you may wonder, we're going to cycle the temperature in these structures. For example, a pile. You're going to inject coal and it will tend to contract, and then hot and it will tend to expand. And you say, what will that do to my soil, pile soil transfer? And it does alter it. And we could go into more details, but let me give you the simple answer. If you have a good factor of safety, you are not in trouble. If you are in a tight factor of safety, it will promote ratcheting. It will begin driving itself deeper down. And it's all about pile-soil interaction. Electromagnetic waves. We see, we hear acoustics, we see electromagnetics. And by the way, the fact that we have both eyes and ears after Darwinian evolution means that both of them are useful. Otherwise, we would have lost either. Right? So both of them are useful. We gather complementary information, and the same in geotechnical engineering. And so what type of information we can gather? Well, this is geophysics. You start with physics, not with correlations. And the physics is Maxwell's equation. It's a beautiful story, but we're running out of time. So let me just say that this is the wave equation. The second variation in space is the first variation in time. So let me say what is the critical thing is that there are three parameters, mu, sigma, and epsilon. Mu is there any ferromagnetism? Sigma is electrical conductivity. And kappa, which is normalized epsilon here, is called the dielectric constant. It's not the best term because it's not constant. So it's better known as dielectric permittivity. So three parameters are important. And we have plenty of techniques that we use for that in geophysics. Time domain for reflectometry, GPR, ERT, EM, SIP. I think I will give some examples of some of them. In the lab, easy measurements with caveats. There's something called electrode polarization, so we can talk about it, but they're quite inexpensive. And once again, it's like adding eyes to our tests. We gain lots of information. So two important parameters when you do wave propagation, like when you in situ, like when you do it with seismic measurements, is velocity and attenuation. This is the equation for velocity. It can get simpler, but this is the one for attenuation, and this is critical. In most cases, in the frequency range that we work, typically in the near surface, the penetration is very short. You don't need to go to the field to determine this. Just with a small specimen, electrical conductivity plays a critical role. You will know whether you have a skin depth or not. If you are near the sea and it has salt water intrusion has taken place, your skin depth is going to be 5 centimeters. Infrared radiation, we feel the infrared radiation and heaters very well because the skin depth is 2 or 3 angstroms, where we have all our sensors. And the potato, don't go for large potatoes in the microwave oven because the skin depth is 1.5 centimeters. So a very large potato will be raw at the center. It's all about penetration. Now, one of the problems with penetration is if there are ferromagnetic quantities, because this is already simplified, sorry about that, but if you have ferromagnetic materials, it will really kill the skin depth. And how can you test that? You don't need anything expensive. Just take a magnet, put your dry sediment on top of a piece of paper, move the magnet. If the particles are moving, you are going to be in trouble. For example, this is the fly ash coming from the Kingston fossil plant. You cannot use GPR. No skin depth. The dielectric constant or the permittivity is very informative with respect to how much water you have and whether the water is able to move around. And so it's going to tell you volumetric water content if it is not frozen. We can go back to the microwave oven and trying to heat the frozen chicken, but that will be, ask me that question in the question and answer. It's a fun one. Okay, if it is frozen, it really drops down dramatically. And for example, that is very important because you can see through ice, or you can see how far, if you are doing a freezing technique for ground improvement to drill a tunnel beneath railroads that they don't like much movement, then you can see how far the freezing front has gone to see if you have enough for support. So very good at that. Electrical conductivity. Remember we said that water dissolves salts and hydrates the ions, and the ions can move. This is electrical conductivity. And either you have salts or you have lots of clays. The counter-ion cloud, the diffuse double layer, moves relative to the clay. In either case, conductivity goes up, skin depth goes down. And in a very predictable way. So let's see some of the things that we can do. If you just take this is truly hypodermic needle. We put a copper wire into it, and then we fill it up with epoxy. We shave the tip, and we push it through a varved clay. This is an X-ray of a varved clay, the winter, summer, winter, summer, winter, summer layers. And this is from New England, right? And this is what the electrical conductivity shows you. It picks up all this. So that means that really, the electric cone where you have a couple of electrodes, and it can be very informative. What the community is probably most familiar is with electrical resistivity tomography or electrical resistivity measurements in the field. And you see these regions here is because you don't have enough information in that region. This is an inverse problem. If you keep that region, all the garbage from the invasion gets dumped here, and it gets very misleading. So I mentioned saltwater intrusion. This is probably a useful thought to have. GPR now fits in any car, in the trunk of a car. And it is such a wonderful tool. In most cases, it doesn't work. But it is such a wonderful tool that I think is worth trying in most cases, because sometimes it works for surprising reasons. For example, this is saltwater intrusion. So you are moving from the ocean, well, it must be the other way around, into land, and you have good penetration, then blind. That is where the salt water has invaded, let's say in New Orleans or in any coastal area around the country. Very important, 70 million people will be affected in the US alone, by sea level rise and coastal implications. And as I said earlier, if the water is frozen and it doesn't move, the electromagnetic wave goes through without attenuation. So now the skin depth can be very large. And so these are some airplanes that were left in was it in Iceland? I think in Iceland, after the war ended, and some group decided to go and find them, so they used GPR. These are skis. This here is the GPR, and you just pull it, and you see the reflection 70 meters down. 70 meters down, you see the reflection from the planes. Huge penetration. And then they went in with steam. They recovered the planes. They took them up to the top piece by piece, and they flew them again. And of course, after 2020s, now we put GPRs also in drones. And we do that with various technologies. I will close this series of physical examples with nuclear magnetic resonance. It has made a revolution in the field of medicine. There are more than 15 Nobel Prizes in this field, and is beginning to catch some momentum in the geophysics community. Let me explain a little bit how it works. The title is very descriptive: nuclear magnetic resonance. You're looking at the nucleus, magnetically speaking, and you're targeting resonance. And that's what we do. So the protons are rotating, spinning, they create a magnetic field. You impose a magnetic field, they get aligned, then you whack them to the side with another magnetic field, and you turn that one off, and you see how long it takes to recover to their original alignment. That's basically the technique, the relaxation time. That is called the T2 time. What can we measure? This is the relaxation of bulk water, water in sand, water in glass beads, water in kaolin, water in bentonite. It's telling you pretty much pore size distribution. So it's telling you several things. First of all, how much water you have. Is the water frozen or adsorbed? And what is the pore size? So it can be very informative. Think of any problems where this may be relevant to you. And pore size is the one that determines hydraulic conductivity. So it may have significant relevance. And my colleague Jorge Macedo is now using the Vista Clara tool. So now we have NMRs that are in a probe that you can bring it down to the field. And then Fugro has a cone with X-ray fluorescence, so they can do elemental analysis as you go through. And so I didn't have more time to cover more technologies, but I just wanted to inject some of those. I mentioned that processing is important. It's not only understanding the physics of what you measure, how you process is important. And look at all these beautiful examples. This is a picture of an actual real picture. This is not AI generated. This is a collection of pictures I have before AI. And so you see these guys rowing and how the circle's beginning to interfere, constructive and destructive interference. And one of those characteristics of wave propagation. This is a boat in Puerto Rico, and there were waves coming from the bay. Where the boat is, there is a dead zone. And then it recovered. That is called diffraction healing. That's the reason why sometimes we don't pick up defects in piles when we knock them from the top, because it goes back. By the time the wave front comes back, it has healed. Then you see when there is a reflection on a plane, you would expect to be a point reflector. But if you look at the images from Van Gogh, one called La Nuit from Van Gogh, you see the lights are reflecting on the lake, not at one point, at multiple points, because it reflects from every crest of every wave. That's called Fresnel ellipse. I could list a large number of physical phenomena, which makes it tricky. Tomography is very powerful. We know that from medicine. That was a Nobel Prize as well. Let me tell you briefly how it works in a very trivialized manner. By the way, if you are a fan of Star Wars, there was a case that they lost Mr. Spock, and they found it with this. So imagine that I have an unknown here. It could be, we actually developed this for the tunnels in the Korean demilitarized zone. We tested with that data. Imagine that there is a cavity here. Very difficult to detect cavities because of diffraction healing. But in the simplest of all cases, imagine that I could illuminate with a light bulb, long tube here, illuminate, and I see a shadow. So, there must be something in between the source and the projection screen. Now, if I could also illuminate from the top to the bottom, so, there is a shadow here. So where is the object that is creating the shadows? Where I backpropagate the two shadows, and where they intersect, that must be where the cause is. That is tomography when you put this in mathematical terms. And so that is the case. And now we can combine. We said the shear wave velocities were assessing stress, the mean stress on the polarization plane. And now we have tomography. Now we can bring the two together. And imagine that in this container now we have lots of sources and receivers of waves, and we make one sound and we pick the wavefront in all of the other ones, and we repeat for the different configurations. And then we do tomographic inversion, and I can pick up the fact that at the center I had a party balloon, one of those long balloons that I had pressurized. And you see the effect on the stress field. Now you may say, come on, this is a very academic exercise. So we went to the Maracaibo Lake. That was before all the situation. This is 30 years ago now. We went to Maracaibo Lake because of production of petroleum. There has been subsidence. Right now the subsidence is almost 8 meters in the deepest part. And so they began building earlier on. They began building this dam, this embankment, and they kept building it up, and it's very unstable on liquefiable ground next to faults. Not a good combination when you have 2 or 3 cities in the potential flooding region. And so we went and did tomographic imaging, and if you interpret them from a point of view of a stress field, you realize how the dam is arching and is changing the state of stress. Conclusions. To summarize what I have said, and the reason why I followed the order that I did, is because some techniques are much better at picking up what the mineral is doing and what the granular skeleton is doing. And you can generalize this now as the rock fracture system is doing. Some techniques are much better at checking how the fluid is feeling and what type of fluid you have. And you can even fingerprint the fluids that you have. And it's a combination of the two that is so insightful for us geotechnical engineers. So we started with the upper part of this chart, the trends in geophysics and geotech. I really think that there is a potential paradigm shift here that goes from sparse point measurements to getting spatial temporal multiphysics subsurface models. And geophysics can contribute to these digital ground models, the digital twins, etc. This is where we're moving. And geophysics can bridge the distance between boreholes and bring the multiphysics into the data fusion. Data fusion has always been one of those nightmares in geophysics. I think that now with machine learning we can do it very well. But folks, everybody's talking about machine learning, but what the revolution that we see happening today is not machine learning. It's a confluence of 100 years of developments, 100 years of data, a revolution in sensors, a revolution in IT, communications, data processing, transmission, memory, and machine learning. We are converging at that time in history where all this is now becoming more possible than ever before. There are places where you can find us and see some of the things in more details. I have to say that this is the product of 3 or 4 decades of teams working and developing this. It has been wonderful. I'm so grateful to the Geo-Institute for giving me the opportunity to visit all of you around the country, and to Kiewit and to you, Shahbaz. Thank you so much. Thank you all for coming.
Pull up some chair for us, and then we'll start the Q&A session. So we have some goose mics, so if you want to ask a question, just press the button.
Yes, please go ahead.
I have a geophysics colleague. One of the technologies that are burst on the scene are the fiber optic sensing systems. And I'm just curious what your opinion or experience with the FOSS.
Let me repeat just in case it didn't go into the system. The revolution taking place with fiber optics and the implications in our field. So it's not an area that I have hold any expertise. I have not used them myself, but I have been observing colleagues who do it, from Dante Fratta in University of Wisconsin to some of the measurements that Kenichi So and his team are doing at Berkeley, and many other people around, right? And let me make a little bit of an appendix here. Many of my students are wearing these smart watches. And I have been quite skeptical of them, as I tend to be very skeptical of new changes, and then I embrace them. But anyway, so then they show me data that these smartwatches that tell you whether you slept well or not. I know whether I slept well or not, or so I thought, or all of a sudden they are saving lives. Because the quality of the data is not that great. It's not like putting you in an EGC or electrocardiogram, right? But it's continuous. And all of a sudden, there are proven cases that they have saved lives. I think that is a little bit of an introduction to fiber optics. The quality of the data, at least as of today, is not the quality of the data that you get with a perfectly coupled geophone or hydrophone, etc., but is so extensive that the opportunities for us to gain physical insight is truly wonderful. And it's not only for acoustic sensing, but now, depending on how we couple, we can measure moisture changes, chemical changes. I think that the technology is developing very fast. It used to be very expensive. I remember when Kenichi Soga was starting, he was talking about tens of dollars per foot and then for the fiber, and more than $250,000 for the analyzer, and all that now is in cents per foot and then much simpler analyzer. So it's one of those that we need to keep our eyes open. This whole distributed acoustic sensing, DAS. So great opportunities. And maybe there is somebody in the audience who has used them and has more insightful comments. Please feel free.
Any more questions?
Yes. Of course, yes, I would love to. I would love to hear, by all means.
So Sujani, you can unmute yourself and ask the question.
Okay. Yeah, Dr. Santamarina, thanks for the presentation. It was very interesting. I have a question about soils in Georgia, where I am. We have a lot of micaceous silty sand type of soils. And my question is, you showed that shear velocity does very well for soil properties estimation. So my question is, does mica interfere with shear velocity measurements like seismic refraction tomography or something like that?
Yeah, that's a very good question. And may I ask you to send me an email, and I will reply with a couple of publications related to that. We measure that with Hyun-Ki Kim. And so there are, mica is fascinating material, but micaceous sands have a property that when you begin shearing them, the mica platelets become aligned, and if you have a sufficient number of them and they are sufficiently large compared to the grain size of the sand, now they form a specular plane, like a mirror, and leads to massive landslides with very low residual friction angle. So if you have micaceous sands in probably more than 4 or 5% of mica gravimetrically, and if the mica platelets on average are the size on or larger than the grains, than the D50 of the sand, you have to be careful for larger strain effects. Now, even if you are not going to experience larger strain effects, if this is a system that is not a problem of stability, now imagine when how mica gets deposited when there is a fluvial deposition. Let's say here comes the sand grain, then comes the mica. The mica sits on top of the sand grains, and then comes more sand grains, etc. But that creates like a bridge on top of the sand grains, and that lowers the stiffness of a sand grain skeleton in the absence of mica. So that is what the mica does. It's a little very, very deformable platelet that softens the material overall. And so to summarize, it does affect the shear wave velocity or the P wave velocity in your material. If you are concerned with larger strain effects, be very cautious. Will you see it with seismic measurements? you don't see the mica plate. Your wavelength is going to be tens of meters, and your mica platelets are millimeters, so you don't see them. It's part of the equivalent continuum, but it will affect the macro scale property. It wasn't very specific answer, but that's all I can say. But if you send me, I'll send you data. We have, I think, very nice data. And if you look at other papers, please, the conclusions may be contradictory just because they didn't specify clearly whether the mica was larger or smaller than the sand grains. So separate the papers according to that very simple geometric ratio, and everything else will make sense.
Thanks a lot.
Thanks, Sujan, for your question.
Yes.
Right. Let me give you a mic real quick. So we are recording this session, so.
Yeah, thanks for the introduction of a lot of more advanced methods than just drill a hole in the ground. Mm-hmm. So could you speak in the context of how it interact with the other part of civil engineering, like structural engineering? We need a design foundation. You know, decades ago, we just do a hole in the ground, and then we do an empirical report. But now, you know, I know people are using ground penetration radar and all that, but there's more advanced technology. Could you speak on, like, how do you see the progression, how that get actually into a huge project like what Kiewit's building, and how they save investors money, like by applying those advanced technique? What's the status now? What do you see that in the future? Thank you.
Yeah, very good question. It's a very open question. So let me try to throw some thoughts. First of all, very recently I conducted a simple questionnaire, and I reached out to basically all my friends in the industry in Georgia and around the country, I have to say. And I concluded that the community, the small size companies remain very conservative and very classical. Even tests that you would test that are not necessarily sophisticated, that everybody has done in college, they are not necessarily being used in practice. And then I saw another group of companies, and then you guys fall into that group, where the advanced technologies and the machine learning concepts, the extensive sensors utilization is now part of the practice. In some of the companies, and I have those slides somewhere, in some of the companies, in fact, it is not whether go ahead and see if you can use AI. It's mandatory to use the in-house AI tools that are available today. So there seems to be quite a separation in the community between the small-size regional companies and the larger-size companies. By the way, there is also a perception that came up from the questionnaire that one of the reasons why they don't use geophysics that often is because they are very expensive. And so for those of you with geophysical companies, I think that there are opportunities to break into the market more effectively. So what seems to be building up is this idea that you are creating, I hate to use words that are becoming popular, but we are creating this equivalent digital analog, the digital twin of the subsurface. And now this leads us to a very interesting thing. In 1969, Ralph Peck, this is history for many of the young people in the audience, but this is a good one to know. In 1969, Ralph Peck finally synthesized something that he had been working with Terzaghi for 30 years, what is called the observational method. And it is a concept that if you have limited information, you make the best design with the information that you have, and then you design accordingly, but with alternatives, just in case that is not the case, and you keep measuring and monitoring, and you keep adapting it. Now the observational method in this scope is on steroids, right? Because now you have all the sensors and you have all the numerical tools running in parallel, and in three-dimensional complex coupled process simulators or proxy that have been trained with those simulators, and now they are AI proxies. So I think that is where we are evolving. But let's be clear, this is not everybody in the community. The small companies do not need that level of sophistication or cost demands, and so there is a little bit of a polarization in the path our field is taking. That being said, I think that the small companies will benefit dramatically from the developments. For example, there are more and more efforts to develop machine learning tools to use the large amount of data available for the last 100 years to better predict material properties. Your complex simulators here will benefit from that, and the small COMSOL or whatever runs the small companies are doing, or even back of an envelope computation, will also benefit from that. So there will be a trickle-down effect benefiting the smaller companies, but there is a polarization taking place.
Thank you for your question. I have a personal favorite. So for a thermal conductivity application for underground power cables, where the cables are going for hundreds of miles, right? And we are talking about the ultra high voltage power cables. So they're big in diameter. How is the interaction doing with the seismic waves, and what are the applications of geophysics in that?
So this is an interesting problem because when a cable is traversing, the losses on the cable are basically converted, all of them, to heat. And so any resistive loss becomes heat. That heat has to be dissipated in the ground. Now, water doesn't like heat, so water walks away from the cable. Now, remember what we said, that thermal conductivity improves with the presence of water. Now, if water walks away from the cable, the thermal conductivity decreases. The thermal conductivity decreases, the cable gets hotter. And that's a problem, the runaway effect that may happen, right? So, so critical here is to assess the ground in its true condition, and probably the worst condition and drier times, right? Or probably to develop a coupling that when you bury the cable, you have an inner layer of high thermal conductivity that is not moisture dependent.
Like a controlled backfill you're talking about?
Yes, the backfill that you're going to use, right? Now, you want to make sure that one will not be moisture dependent, because the cable will be running in the dry season and the wet season, right? And now, will seismic well help you find it? Indirectly, in the sense that where it is drier and your suction is changing, you may have higher shear wave velocity. It's not an obvious. You want to use the measurement that is most sensitive to the parameter that you're exploring. For example, GPR, if it has penetration in that area, will be more informative than a seismic wave.